we'll start the next tutorial, which is on how to store extracellular electrophysiology data, such as your raw recordings, your LFPs, your spike times in NWB using PyNWB and MatNWB. You can follow along on the PyNWB tutorials page by going there and then going to domain-specific tutorials, and it's the first one listed there. Okay, so we're going to cover how to create an electrodes table, how to add acquired raw voltage data to your NWB file, how to add LFP data to your NWB file, and your sorted spiking units. Yeah. Okay, so to start, we will create an NWB file just like we did in the last tutorial, passing in all of these keyword arguments and whatever additional ones you'd like. And to store extracellular electrophysiology data, we must first create an electrodes table describing all the electrodes that were used to generate this data. These electrodes are stored in a dynamic table that is named electrodes, and it will go in a special place in the NWB file. And you can see in this diagram here, what is a dynamic table. It is a data structure that has a name, a description, and any number of columns of type vector data. And vector data are columns that have a name, description, and data. The electrodes is a specific instance of the dynamic table, generic dynamic table, and it specifies that there are columns for the XYZ location, the impedance, the brain location, any filtering that was applied, and on what electrode group these electrodes were part of. And most of these fields are optional. But what is not optional is that the electrode requires an electrode group, which usually represents a probe or a shank of a probe. And these reference a device, which can be your probe or your array, for example. And so to get started, we first need to define a new device object using nwbfile.createDevice. So we'll call that there. And we're going to create a device for an array and give it a name, a description, and provide the name of the manufacturer as well. So now we have a device object. We can create an electrode group, and then we'll add electrodes one at a time using add electrode on the NWB file. Because this is a dynamic table, just like we described earlier about the trials table, we can add any additional metadata to this electrodes table that is maybe specific to your lab or your experiment. And so in this case, we're going to add an electrode table column and called label to the table. So we'll call add electrode column, give it a name and a description. And now every time we call add electrode, we have to provide a label. And now here is some code that we will, here's some code to loop through the creation of 4 electrode groups, 1 per shank, and we're going to add 3 electrode channels or 3 electrodes per shank. So we'll just go looping over the shanks. We'll create 1 electrode group by calling nwbfile.createElectrodeGroup. And there are a few required fields, such as the name, the description, the device that we created earlier will be linked in this way, and a location, the location in the brain. And then we'll loop through the number of electrodes that we're creating per shank. In this case, it'll just be 3. And we'll add an electrode by specifying by linking to the group that the group that this electrode is part of. And we'll specify a label because we added a label column earlier. and say what brain area this electrode is in. And this will create 12 electrodes across 4 electrode groups for our one device. And these will be part of the NWB file already because we're calling the methods off of NWB file. Similarly to the trials table, we can view this electrodes table in tabular form by calling .to data frame and getting a data frame, and we can manipulate it there too. Okay. So now we have 12 electrodes that we can reference when adding our raw data to our file. Raw voltage traces and LFP data are stored in electrical series objects. These are subtypes of time series, but they additionally specify that the units of measurement are in volts, that the array has dimensions time by channel, and that we have an additional array of electrodes, an additional array of references to rows of the electrodes table to indicate which rows or which electrodes were used in this particular recording. So we can have more electrodes that were used in a particular recording in the file. Like you might have the first 10 were recorded in the first half of the file, first half of the session, and then you switched electrodes or inserted new ones still within the same session, and you have a new time series that you want to reference to the 11th to 20th electrodes, for example. Or perhaps some electrodes are broken and you have no data for them and from the machine. So to create this electrodes reference array, we need to call NWB file.create electrode table region. And when we pass in for the region argument, a list of indices of the electrodes table representing the electrodes that we want to use. In this case, we're just going to use all of the electrodes. So it'll go from 0 to n-1. And we're going to pass this into our electrical series next. This shows what I just described earlier, that an electrical series is a time series. It has a name, description, data, and either a timestamps array or a rate and starting time. But additionally, it specifies that the unit must be in volts, and that we have an array called electrodes that is this dynamic table region that refers to particular rows of our electrodes table. So we'll create our electrical series in much the same way as the rest of our neurodata types by calling the constructor and passing in keyword arguments. So we'll have the name, data. Here is our electrodes reference, which is what we created up here. And then in this case, we'll say that our data were sampled regularly, starting at the session start time and at sampled at 20,000 hertz. Okay, so this raw electrical series object variable here is our electrical series, but it's not part of the NWB file yet. So to add it, we have to decide where it goes. And because this electrical series represents raw data, we're going to put it into the acquisition group. So we'll call NWB file.add acquisition and put in our raw electrical series. Now let's cover how to add LFP data, local field potential data, to our file. These are also stored using an electrical series because they are voltage measurements over time. So we're going to create a new electrical series. For this fake data, we're just going to for this example, we're just going to use fake data of 50 time points across 12 electrodes. And constructing this works the same way. You pass in name, data, electrodes, starting time, and rates. Now to help external tools for data analysis and visualization know that this electrical series is an LFP rather than raw data, we will store this electrical series inside of an LFP object. This is very similar, analogous to how we store our spatial series object inside of a position object in the last tutorial. So LFP is just a container over the electrical series. And we can do that by just calling the LFP constructor and passing in our electrical series. Now we have an LFP object. Now, unlike the raw data that we added to the file earlier in the acquisition group, LFP data is typically considered process data because the raw data has been filtered and downsampled to generate the LFP. So we're going to add it to a processing module within the processing group of the NWB file. To do that, we will call NWB file.createProcessingModule, pass it a name. Because this is extracellular electrophysiology data, we're going to use, by convention, the name ECEPhys and give it a description. This processing module is already part of the NWB file, but it's empty. So we're going to call add to add our LFP, which contains our electrical series of data inside of it. Next, let's add spike times. So let's say we've collected our raw data and we've run kilosorts or mountain sorts or some other spike sorter, and we have sorted units now with their spike times. Adding the units data are stored in a units table, which is a subclass of dynamic table, just like the electrodes table and the trials table. So we can add columns to these, to add additional metadata that are not part of NWB, the core schema. So we can do that by calling NWB file.add unit column. And it will be name, let's say we're adding a column that describes the quality of the sorting. We'll say name equals quality, description equals sorting quality. And then let's generate some random spike data and populate this units table by calling add unit. So we'll just loop through 10 units and create some fake spike times. And we're going to call NWB file.add unit, spike times equals spike times. And this unit, or all of these units, will just say that the quality is good, because this is now a required field, given that we've added quality as a new column for the units table. Just like the other tables, we can convert this table to a pandas data frame for easy visualization by calling toDataFrame. Okay. If you have other types of electrophysiology data, or you want to store like your threshold crossings or your waveforms, then you can do so in several other types for such as for event detection or event waveform, or using the waveform mean column of the units table. And you can read about that in the tutorial here. Finally, we can write this to file, this data to a file, just like in the last tutorial. We call with NWB HDF5 IO with a file name and W as the mode. And we call io.write to write this NWB file to disk. To read it from disk, we will do much the same as the last tutorial. We'll create a new IO object within the mode R for read. We'll call io.read, and then we can access the different elements in our acquisition group. Our raw data is stored under an electrical series named electrical series, so we can access it by name here. In our LFP electrical series data is stored under processing in a module named ECEPhys, and then nested in an object called LFP, and then in the electrical series object named electrical series. And just like I described earlier, these data, the actual data arrays are loaded lazily, only on demand. If you use a colon to index the data array, you'll get all of the data elements, which can be a lot, or you can slice it in any of the dimensions to get just a small section of that data array. Similarly with tables, you can call red NWB file.units to get the units table, and index a particular column, let's say the spike times, and then a particular row. So this would be a particular unit, the 0th unit, to get all of the spike times from the 0th unit. Alternatively, you can convert this to a data frame and then use pandas methods to access the spike times from the 0th unit. And that's it. So we covered how to create electrodes and electrode groups and your probe device in the NWB file. We covered how to add raw data to your NWB file from your electrodes. And this can be raw data and LFP data as well. And we covered how to store the spike times of your sorted units and any additional properties you want to store about your units. Okay, I'll now pass it off to Ben to cover much the same material, but using MatNWB instead. And I'll take any questions as we transition.
Okay, so I'm going to go over the MATLAB tutorial for extracellular electrophysiology. Again, it's going to be pretty similar to the tutorial that Ryan just went through. I'm going to try to highlight some of the differences between MATLAB and Python. So we're going to be adding a voltage recording with local field potentials and spike times. All right, so the first thing we need to do is create our NWB file object. This is basically the same as the command from the intro tutorial. And okay, we're just going to get right into creating the necessary metadata for adding extracellular electrophysiology data. It does take a bit of preparation. Basically, if you want to add an electrical series, you need to add an electrodes table first. And so in order to create that electrodes table, which is an instance of a dynamic table, you need to create electrode group. And in order to create electrode group, you need to create device. So what we need to start with is creating a device. So let's do that. So we're going to create this electrodes table as a dynamic table object. Here, calling this is a bit different. It's types.htmf common.dynamic table, because this is HTMF is the underlying library of NWB. It kind of it defines a general framework for hierarchical data structures. And it's not like neuroscience specific. And so NWB built on top of it, but there are some types that we take directly from the HTMF library, and this is one of them. So this is how you access dynamic tables directly. We'll define the column names, location, group name, and label. And there are a number of other ones you can put in, such as like the XYZ position. You don't need to do that, but it's options that you can add. And then we'll just, as a description, call this all electrodes. And then we'll create a device from types.core with a description and a manufacturer. So again, this is where you set the name. So nwb.generaldevices.set, the name of the device here is array, and then we're assigning that to the value here, which we just created. Okay, so now we want to iterate over 4 shanks and 3 channels per shank, just to create this example electrodes table. So I'm going to iterate over shanks, create a group name, which is just shank 1, 2, 3, 4. And within each shank, I'll create an electrode group. So the electrode groups, basically, they define groups of electrodes that you would use together for spike sorting. So if you have multiple shanks, you would have multiple groups. For lots of modern probes like NeuroPixels, you wouldn't necessarily need to have multiple groups. You could just have one group. But let's put multiple groups for now. So, okay, we have an electrode group that we're defining a description, which we're using the shank group name as part of the description. Location, it refers to a brain area. So you should put like an actual brain area here, not just the string brain area, but you should put like the abbreviation of like the actual brain area where this group is. And then this is a new type of thing. It's a reference. So this is a type of reference. It's kind of automatically done in PyNWB. MatNWB, you have to be a bit more explicit. So you would do types.untypes.softLink, and then you direct it to the device object. And this basically says create a soft link to device. So you're not putting a whole device object in there. You're just creating a link to the one that already exists. And okay, so then we need to set this electrode group inside of this general extracellular ephys group within the NWB object. And we're going to set it by the shank group name, which we set right here. And then for each of these shanks, we'll iterate over the number of channels per shank, which is 3, and add a row for each one of those. So again, we've got location, we have group, which is another type of link. So the difference between soft link and object view is soft link is just one reference to an object, whereas an object view actually creates an array of references. So here, where each of these attributes is going to become a column of our table. And so group is a data set, and each element of that data set is a reference to the electrode group. And then we have the group name, and I'm just adding label to show you that since this is a dynamic table, you can add columns to it. So location, group, and group name are kind of default columns, but you can add whatever columns you want as long as you declare them here. And here I'm saying, okay, label, which is often a useful attribute for electrode tables because often you do have labels for these electrodes. And so I'm going to print out a special label that takes into account the shank group and the number of the electrode in this iterator. And then again, you can do a nice little printout of this table using this toTable command, which really doesn't do anything except for converting this MatNWB specific dynamic table object into a MATLAB table object, which is a built-in type now in MATLAB, which allows you to print it out nicely. But to actually add this to the NWB file, you would do nwb.general extracellular ephys _ electrodes, and then you'd set that to this electrodes table. And now you've added that to the NWB file. All right, there's a bit of text here about object views, which I went over briefly. Okay, now that we've added our device, our groups, our electrode table, now we can finally add the actual electrical series data, the voltage data over time. Now, just like spatial series, an electrical series is a subtype of time series. And all it really requires, in addition to the data and the timing information, which can again either be starting time and rate or timestamps, is a reference to the dynamic table called electrodes. So that reference is built using a type called a dynamic table region. So this again is part of the HDMF common library. And dynamic table region is a way of referencing specific rows of a dynamic table. So basically what this allows you to do is to specify, okay, you have all of these electrodes in your table, which electrodes are corresponding to the electrical series. Now, a lot of the time, you're just going to have it, all of the electrodes in the electrodes table are being recorded from. And so you can just do what I'm doing here, which is to create a table, to create this dynamic table region. The first thing you want to do is say what table you're referencing, and that would be the electrode dynamic table. Then you give it a description, and the data here, this is the rows of that table that you want to index. And in this case, it's all the rows. This is indexing starting at 0 for consistency with Python, which is maybe a bit foreign for MATLAB users. But this is how you would do that. you're just iterating from 0 to the length of the electrodes table -1 because you started at 0. And yeah, so here's basically what we're adding here is just simply this electrical series data type, which inherits from time series and references the electrodes table. So we'll do that here. This looks a lot like creating a time series, types.core, but instead of time series, it's electrical series. It should be in volts, and it is referencing the electrode table through this dynamic table region that we've created up here. So the length of the dynamic table region should match the first dimension. Remember, because in MatNWB, the dimensions are reversed. So now this is time and this is electrodes. So this should be the same length as the data array here, which it should be. Okay, so once we've created this object, we can then add it to the NWB file. I'm going to add it in acquisition. Usually that's where electrical series go. Not always, but usually. So nwb.acquisition.set. Again, this is how I set the name. This could be anything, but best practices currently is to just name it the same name as the name of the class itself, unless you have multiple of them or you're in some kind of situation where some additional descriptors would be helpful. If you're not in any of those situations, then you can just default to this. Okay, and this will add it to the NWB file. Now, LFP. It's going to be very similar, actually. This is a big, intimidating diagram, but most of it we've already gone through. So LFP is actually like a container that contains electrical series. And it can go into a processing module. So we're going to create a processing module called EC-EFIS, an instance of the processing module class, and we're going to put LFP inside of it, and then put a new electrical series inside of that LFP object. So let's go through that here. We're just going to use the same electrode table region, which is fine to reuse that. And then we'll create this LFP object, and we're adding, as we're creating it, we're adding an electrical series named electrical series. And then we have this EC-EFIS module, which we give a description, and then we can say EC-EFIS module dot NWB data interface dot set, and then we add this LFP with the name LFP in all caps, and then NWB.processing.set. We can add the EC-EFIS processing module to the NWB file under the processing group with the name EC-EFIS. So now we have our raw electrical series data that's been acquired, and we also have the LFP data, which is marked as LFP because number one, it's in a processing module, and number two, it is contained within the LFP neuro data type. All right, so next we want to add spike times. So you would think that this would go in the processing module. It can go in a processing module, but there's also like a special place for it in the NWB file. So first, I'm just going to generate some data. Here, I'm doing it in a cell array because that's the thing about spikes is you can have a different number of spikes for each neuron. So okay, we'll say our first neuron has 22 spikes, our second neuron has 21, our third neuron has 19, 16, 26, etc. So what this creates is something that we call a ragged array, where you'd like to put these all in an array, but the thing is they have different lengths. So you can't do like a standard rectangular array. And that's what we call it, a ragged array. So NWB has a special way of storing this data, where essentially what we do is we take all the data and we stack it up into one really big array here. And then we use the second data set that just indexes into this array and tells you how to split this up into a ragged array. So if you had, you want to express this, where you have these green values as the 0th neuron, the purple values as the first neuron, and the blue values as the second neuron, you'd put them all in a row, and then you would just give, in this second data set, give the length or I guess the cum sum of the length of each of the spike times arrays. So we have a convenience function to create this for you. It's util.create indexed column. So all you have to do is input this cell array of spikes where you separated out the spikes into individual cells, and then we can create these data sets for you, so you don't have to worry about it. Once you have that, you can use the types.core.units neurodata type to specify a units table. A units table is, again, a type of dynamic table, so you can add your own custom columns if you want. I'm not going to demonstrate that here, but it's done in the same way as it's done in other classes. So here I'm just going to put the spike times, put a description, and then I'm going to give it the spike times vector and the spike times index, which are created from this create indexed column. Which then creates the units table. And here I'm just assigning it directly to the NWB file, which you can do. It's a bit more convenient. So I'm saying NWB.units. This is the special place for the units table. And I'm just assigning it directly to this value. Okay, so just like before, NWB export, you've got this big NWB variable, which holds all of this data now, your electrical series, your LFP, your electrodes table, your spike times. It's all in this NWB object. So you write that to this path. Then you can read it back out. You can access data sets, but of course, you won't get the data unless you say load, which will actually load all the data. And here with electrical series, you actually often are in a case where you might not want to load all of those into RAM all at once. So again, here's how you would load just a piece of that data. You just do, you traverse through the hierarchy of neurodata types. And then once you get to the one that you want, data, and then you just index it. And that will automatically only read the chunks of data, if it's chunked, that contain the region of data that you want. Or if it's not chunked, it will only just only read the data that you've asked for. And then I just wanted to show how you get specific spike times, because the syntax for this is a little tricky. So it's nwb.units. You can say get row of a table, and then you can get the spike times attribute of that and get the first element of that, and that will give you an array of spike times. And so you just change this number to give you the spike times of different rows. Okay, and that's about it. Any questions for MATLAB extracellular electrophysiology?